In this video, we're going to look at the basics of counting, and we're going to focus on the 4 rules associated to the 4 mathematical basic operations of add, subtract, multiply, and divide. We're going to start with the product rule because it happens to be pretty straightforward. So a procedure can be broken down into a sequence of 2 tasks. If there are n sub 1 ways to do the first task and n sub 2 ways to do the second task, then there are n sub 1 times n sub 2 ways to do the procedure. So an example of this is how many outfits can be made with 4 shirts and 3 pants, assuming everything coordinates. So here's the idea. The first task in this case is putting on a shirt. And since there are 4 options, there are 4 ways to do that. The second task is putting on pants. And since there are 3 options, there are 3 ways to do that. So we can use the product rule, and we would just say that 4 times 3 would give us 12 different outfits. How many bit strings of length 7 are there? Okay, so in this case, what we have are a string of numbers that consists of zeros and ones. 4, 5, 6, 7, and there are 7 of them. So each one represents a different task, and the task is picking whether it's going to be a 0 or a 1. So for the first part of the string, or the first digit in the string, there are 2 options available. It could be a 0 or a 1, and that's the same for every single one of these. And therefore, we end up getting 2 to the 7th number of bit strings that are length 7. And if we plug that into the calculator, that'll give us 128 strings of length 7. That's an 8. All right, let's try another one. How many different license plates can be made if each plate contains a sequence of 3 uppercase English letters followed by 3 digits? Okay, so for the letters, if you didn't know, there are 26 letters possible in the English alphabet. For the digits, if we're talking about a license plate, we could have anything from 0 up to 9. So for the digits, then we would have 10 options because 0 would count as an option. Okay, so if we are making a license plate that has 3 letters followed by 3 numbers, for the letters, there are 26 options. They can have repetition. And same for the numbers. They can repeat the same number every time. That's fine. So that would give us a total of, here, I'm going to write it below, 17,576,000 license plates. Oops. Quite a bit. Okay, so this example is a little bit more theoretical. How many functions are there from a set with m elements to a set with n elements? Okay, so functions, we talked about that all the way back in chapter 1. Let's say we have our domain here. And in our domain, there are m elements, m members of the domain. Here, I'll just put a few dots in there to represent members of the domain. Okay, then we map that into the codomain. And there are n elements here. Sorry, that's supposed to be an arrow, though it didn't look like it. N elements. Okay, so here, let me put a different number. Great. So when we are talking about a function, what makes something a function is that something in the domain only goes to one thing in the codomain. So I never have something over here go to 2 things. It's just one mapping over here. Great. Something like this. In fact, all 4 of these could have gone to the same number. It just couldn't have been that one of them went to 2 different numbers, okay? So the idea is with a function, we're going to base our number of possibilities on our domain. Our domain is limiting us. So here's the idea. We have m elements. And each element can get paired with something over in the codomain, and there are n of them. And they can pair up multiples, right? Like I said, everything could go to one item. They could all go to different items, but they can pair up with anything in the codomain. And that leaves us then with n to the m functions. All right. How about one-to-one functions? So one-to-one functions. Now it's probably been a while, but one-to-one means that we won't have any sort of repetition. In other words, we couldn't have the map where everything in the domain, let's do 3 of them, goes to only one thing over here in the codomain. That's not going to happen. That's not one-to-one. Okay, has to look more like this. This, in fact, what I've drawn here is one-to-one. All right, so this is no good. We can't have that happen. That's not one-to-one. All right, so what we want then is we still have our m elements in the domain. There's m elements that we need to match up with the elements in the codomain, okay? And the first element has n options, but because we don't want it to repeat, now we're going to change this up, and the next element only has n minus 1 options. Should probably give myself a little bit more space. N minus 1 options. Oops. Okay. Then the next one has less. 2 less than the previous 2, because each time we match one of them up, we take that one out of the possible matches that are allowed. Okay, and that's how we kind of account then that there can't be any sort of double matching with those from the domain into the range. Okay, so we keep this pattern up, ... until we get to... All right, so before I fill this in, I want to just kind of take a second and do a little bit of an example of what this could look like. All right, let's say we have 6 elements in the domain, and we're going to match that up with 10 elements in the range. Okay, so here's what's going to happen. I'm going to have 6 possibilities, okay, for each of the 6 elements in the domain. And for the first element, there's 10 possibilities. Then for the next one, there's only 9, and then 8, and then 7, and then 6, and then 5. And then it stops because I've matched everything that's in the domain to something in the codomain. All right, so this last number here is what we get when we subtract 10 minus 5. But 5 is coming from being 1 less than 6, because we have a total of 6 things being matched, right? 2nd, 3rd, 4th, 5th, 6th. So there's 6 things being matched. And for that reason, then, that last number there is 1 less than the 6 total, because each time we minus 1, that happens after the first number. So here is the first time we actually minus a 1, right? That's our first minus 1. And then we do that again. Here, let me do it in red so I don't have to keep switching. So minus 1 again, and then again, minus 1, minus 1. So we minus 1 how many times? 5 times, 1 less than our total. Okay, so that means then that this last term is n minus m minus 1. So 1 less than total number of m elements, because the first element didn't subtract a 1. And then we get to the last element, which is the mth one. And that means we've subtracted 1 m minus 1 times. All right. And there we go. That's it. Like, I mean, I can put these in parentheses as my final answer, but that's it. That's how you figure it out. This is actually, in fact, the answer here. It's a little bit messy, but there you go. ... All right. This was kind of fun because they started showing what happened with the numbering system for phones when we had an explosion of phones from cell phones, and our population has just gotten bigger. So under the old plan, there were kind of rules that were followed for the area code, followed by the 3-digit office code, followed by the 4-digit station code. All right. So the rules went like this. X could be any number from 0 to 9. N could only be numbers from 2 to 9, and Y could only be a 0 or a 1. So originally, it used to be that the area code was an interesting combination, right? The first number could only be a 2, 3, 4, 5, 6, 7, 8, 9. The second number had to be a 0 or a 1. And then the third number could be anything, any of the digits. All right. So that was the old plan. The new plan definitely changed it. And all it did was restricted the first number of the area code and the first number of the office code. And that allowed more possibilities. So let's see how many different telephone numbers are possible under the old plan and new plan. So let's start with the old plan. All right, so under the old plan, here's what we got. We're going to be looking at this, and I'm not going to rewrite it if that's okay. I'm just going to kind of refer to it. So where it says N, there are, let's see, 8 possibilities, because we can't, so 0 through 9 is 10 possibilities, right? But now we take off 0 and 1, so there's 8 possibilities, and then there's 2 possibilities for this. Okay, cool. So for N, that's going to be 8 possibilities times Y has 2 possibilities, and then X has 2 possibilities. So that's the first set of numbers in the phone number. Then the next set is N again, so 8 and 8 and 10. And then the next set is, so those are the next 3, and then the last 4 are all 10s. So kind of breaking it up. I don't know why I'm writing so crooked, but oh well. All right, so that ends up coming out to 160 times 640 times 10,000, or 1 billion 24 million possible phone numbers. So we exceeded the 1 billion mark and needed more. Plus, you know, there was work phone numbers and all of that fun. Okay, so the new system then allows a lot more possibilities. So now we're looking at this one here, the new system. All right, so N is 8, and then it's times 10 times 10. And then again, we have 8 times 10 times 10. And then the last 4 are 4 10s. So that gives me 800 times 800 times 10,000. Okay, so 800 times 800 is 640,000 times 10,000 is 64 billion possibilities. Yikes. All right. I don't know if they wanted us to add them together. I didn't think so. I think it is just there's 2 answers. So I think that's all they were after. I don't think they mean total the 2, because that doesn't quite make sense. But as you can see, there's almost 63 billion more possibilities under the new system than there was under the old system. All right. Use the product rule to show that the different number of subsets of a finite set is 2 to the magnitude of S. I can't remember if that's how we labeled it in the previous chapter, but remember, this represents number of elements in S. Okay, I actually love this example because I learned something. It's so fun. Okay, so let me show you what nifty possibility there is. All right, nifty possibility. Actually, I'm going to state it and then I'm going to show you. So we can use bit strings to represent all possible subsets of S. Bit strings. Just realized that I said the plural, but I didn't write the plural. Let me do that. Bit strings to represent all possible subsets of S. Okay, let me give an example. I think it actually works out really well to see it as an example. Let's say S happens to be the set 1, 2, 3, 4, 5. All right, and let's say I'd like to represent the odd numbers in this set. In other words, I want 1, 3, and 5 to be the subset, okay? Here's how I do that as a bit string. I basically, and actually, I wish I had, sorry, let me give myself more space for this. I'm gonna write it over here a little bit more. 1, 3, 5. Okay, so here's how you write this as a bit string. What you do then is for every number you want to be included in the subset, you put a 1, and every number that you don't want to include in the subset, you put a 0. So where there's a 1 in S, I'm going to put a 1 there, and where there's a 2, I'm going to put a 0, and where there's a 3, I'm going to put a 1, and where there's a 4, I'm going to put a 0, and where there's a 5, I'm going to put a 1. So this bit string 1, 0, 1, 0, 1 represents that from the subset, I'm picking the first number, the third number, and the fifth number. Okay, so for the even numbers, 2, 4, 6. Oh, just 2, 4, not 6. There's no 6. 2 and 4. That means the bit string I would use would start with the 0, and then I'd select 2, not 3. I'd select 4 and not 5. So that's the bit string that works for that. Okay, so let's say I wanted to do 1, 2, and 3, the first 3 numbers. Okay, that means then the bit string is going to be 1, 1, 1 with 2 zeros. So I'm picking the first 3 and then everything else is 0 from there on out. So I can match up all these subsets with these bit strings. Okay, so what I have done is I have reduced the problem to asking how many bit strings are there? And S happens to have the number of elements that we're going to use this absolute value of S to represent. Okay, so since we're basically going to have, let's say, ... Okay, so this represents absolute S number of elements. And there would be 2 possibilities for each of them, which leaves us to the absolute value of S, or the size of elements in S. And there you go. Nifty. Okay, they do give a product rule for a Cartesian product. It actually ends up working out that you would take all the possibilities for each slot and multiply them together. Product rule is so nice. Okay, moving on. The sum rule. So we'll actually move a little faster through some of the next ones because the product rule is kind of the big meaty one, and then we'll see some less. Now the sum rule is also meaty, so I shouldn't say it isn't. And they came up with some very interesting examples. But here's the big factor in the sum rule. If a task can be done in 1 ways or in 2 ways, so the magic word "or," that gives us that we would add the 2 ways together. Let's look at this example here. Suppose that either a faculty member or a student in a math major can be representing a school. I said that very differently than the first sentence, and I have no idea why. So you can have either a faculty person or a student who's majoring in math, so math faculty or a student who majors in math, to represent a university committee. How many choices? If there are 37 math faculty members and 83 math majors, and nobody is both a math faculty or a student at the same time. So 37 plus 83. That's it. It's just that simple. There's 120 possible representatives. That's it. It's that straightforward, because we're saying one or the other can work. All right. In terms of sets, we have, when we're talking about union of two sets, we can simply add them together, the two sets together, or the magnitudes of their sets together, as long as they're disjoint. Another more general way of saying that, instead of just working with two sets, you could say A sub 1, union with A sub 2, union with ... all the way down to A sub m. And that ends up equaling the magnitude of A sub 1 plus A sub 2, ... down through A sub m. And this works where we're saying for any one of them that we're choosing, A sub I, and looking at it with A sub j, they have nothing in common. So we say that their intersection equals the empty set. And that's for all I and j. All right. Let's look at another one. Suppose, let's see, suppose statement labels in a programming language can either be a single letter or a letter followed by a digit. Find the possible labels. So one possibility is we have a single letter, which means we have 26 possibilities. Or we have a letter plus number combo here, which means 26 possibilities for the letter times an additional 10 possibilities for the number. And again, we're talking 0 through 9. So that's 260. So adding those two together will give us 286 possible labels. All right. Each user on a computer system has a password, which has to be 6 to 8 characters long, where each character is an uppercase letter or a digit. Okay. Each password must contain at least one digit. How many possible passwords are there? All right, let's start with the case for 6, and we'll build our way up. So 6 characters, and they can be either uppercase letter or a digit, right? So uppercase letter, that means there's 26 possibilities. For a digit, there's 10 possibilities. So a total of 36 possibilities for all 6 characters. Okay, so 36 times 36, 6 times. I'm not going to write that out. 36 to the 36. I'm sorry, 36 to the 6. Okay, now they specified that at least one character has to be a digit. So that actually limits the possibilities here, because what I've just considered, 36 to 6, allows that all of them could have a bunch of digit combinations. All right. So, I'm sorry, could have a bunch of letter combinations, and not have digits. And it has to contain at least one digit. So what I'm going to do then, since this is all possibilities, I'm going to subtract out the possibilities where there's no digit at all. That means that I'm only considering letters. So 26 to the 6. So these are no digits. So 36 to the 6 contains all possibilities, including the possibilities that don't have digits in it, and just letters. And then I'm subtracting out the possibilities where we have just letters. And that leaves me with, you can get your calculator out and calculate this, or you could trust me. 1,867,866,560 possibilities. Okay, now that we kind of went through that work, the other two are very similar. We just do 36 to the 7 minus 26 to the 7, and that comes out to 70,332,353,920 possibilities. And then last, the 8 characters, 36 to the, oh, got excited about writing it to the 8. There we go, 36 to the 8 minus 26 to the 8 comes out with 2,612,282,842,880. So if we add those all together, those three summed up, all right, we will get 2,684,483,063,360 possible passwords. Wow. All right, there you go. Okay, let's look at this example of internet protocol. I found this really fun. Looking at the different classes for internet protocol, or the IPv4s, using 32 bits. All right, so they kind of broke it down, and then they gave like an explanation below too. So class A always starts with a 0, and it's followed by a 7-bit net ID, which they kind of wrote as netted in this picture, and then followed by a 24-bit host ID. All right, so series of 0s and 1s for 7 that indicate the net ID, and then another 24 which map to the host. Class B starts with a 1 and a 0, so starts with 10, 1 and 0, and then it is 14 for the net ID, 16 slots for the host ID. And we're talking about, since we're talking about bits, right, 0s and 1s. Class C starts with a 110 followed by 21 bits for the net ID, 8 for the host ID, and then neither class D or E are assigned for computers on the internet, only A, B, C are available. Okay, now they gave us 2 stipulations down here. They kind of crammed it in here. 1111111 is not available as a net ID for class A. Okay, so we can't actually have that happen in class A. So we have one option gone from class A. Okay. Then they say the host IDs consisting of all 0s and 1s aren't allowed either. All right. So when we're talking about host IDs, that means that we have 2 options gone. And that applies to everybody, A, B, and C. All right, cool. So how many addresses are available? Here we go. So let's start with class A. So for class A, we have, let me scroll up here so I can see. So the first number is chosen, which means I'm not going to bother writing it. It's just a 1, like there's a, if I was writing that there's 32 possible slots. Right here, I'll pretend to write 32, blah, 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 32. The first one has no options except the one that they're giving us. And then the next one has 2 options. In fact, the next 7 have 2 options because we're talking about the 7-bit, okay? Okay, so here, let me go ahead and hopefully the computer doesn't get too mad at me and erase that. Okay, good. Sometimes it gets mad at me. All right, so here we go. So for the first option, 0 is assigned. For the net ID, the 7-bit net ID, that is represented as 2 to the 7th, but we know that in class A, one of those is not going to work for the net ID. All right, so we have to take one of them away, which leaves us with 127 for the net ID. All right, then for the host ID, there are 24 bit, so 2 possibilities for 24 different times, all right? And then we have to subtract out the fact that all zeros and all ones are not allowed, because that counts them when we do 2 to the 24. And that leaves us with 16,777,214 possibilities for the host ID. All right. So for class A then, if we're lining these all up, I'm taking those 127 for the net ID and I'm timesing them by the 16,777,214 for the host ID, multiplying those together, and that gives me 2,130,706,178. All right, so that's class A. All right, class B. So for that one, the first 2 are gone, and then we have 14-bit for the net ID. And this time we don't have to subtract 1. That only worked in class A that we had to worry about that. So 2 to the 14 is going to end up being 16,384 possibilities. And then for the host ID, there were 16, but we do have to take off the fact that all ones and all zeros are not okay. So that leaves us with 16,434 for the host ID. So here, I'll just write this for net, and this is host, just so we're clear. I'm getting lazier as I go, so I'm not like writing it all out. All right, so we multiply those together. 16,384 possibilities for the net ID times 16,434 possibilities for the host ID, which gives us 1,073,709,056 possibilities for class B. All right, and then class C. So for class C, the net ID is 21 bits, so 2 to the 21. Again, we don't have to worry about subtracting off. That is 2,097,152 for the net ID. And then for the host, there's 8, but we're going to subtract off 2 for the all zeros and ones. So 245 only for the host ID. So multiplying those together, 2,097,152 times 245 comes out to 532,676,608. All right. And we add those together. And that ends up giving us 3,737,091,842 IPv4 addresses available for computers on the internet. And we will go through the next 2 rules, the subtraction and division rule, in the next video.